The speed of light is the same in every direction. Therefore, an expanding light pulse must form a stationary sphere. Consider a light source at the center of a metal sphere. The sides are removed to see the behavior of the light and its reflections. In a moving sphere, the reflection is deflected so it always returns to the source. Two spheres emit a light pulse as they pass. The light takes longer to return to the moving source. The locus of the points where the photons reach the moving shell is shown. The occupants believe that this locus is a circle. The total length of each path is the same. The locus is an ellipse. The equation of the ellipse gives us the time when the reflection occurs. The geometry dictates that the sphere must be distorted. The distances Vt and Ct give the shape of the sphere. The sphere is contracted in the x direction by the factor gamma. The result is the Lorentz transforms. A sinusoidal signal expands out from the center of the sphere. The signal is reflected back to the source. The two signals interfere, forming a standing wave. The nodes where the signals cancel are marked by circles at amplitude 0. A part of the signal is isolated inside a tube, such as a laser or a telescope. The start of a cycle is marked by the white circle, and the wavelength is measured in the blue tube. The wavelengths are lambda 1 and lambda 2. The emitted and reflected signals are mirror images. The interference pattern is complex, but still has elliptical nodes. When the time transform is applied, the pattern becomes organized again. These results are a perfect match to those obtained in Part 1. Standing waves have successfully explained Einstein's contraction. The Doppler effect can be used to explain the impossibility of keeping clocks synchronized when they are moved. The phenomena is symmetrical. There is no way to identify an absolute frame of reference. In the twins paradox, one twin, cat, stays at home while the second, dog, travels to a distant star. The position where the time in the moving system is t prime is x. There is an infinite plane at each value of t prime, which moves at a velocity of c over v. When v equals 0, the speed is infinite and time is the same everywhere. As the speed of the vessel increases, the planes slow and start to accumulate behind the vessel. This is time that has not yet passed in the vessel. When the speed drops, these planes speed up and time passes faster in the vessel. Time is the same in both systems when the speed returns to 0. We can also analyze this using numerical integration to calculate the speed, distance, and time in a moving system. In the first example, the acceleration is a cosine cycle. This is easy to integrate to get the velocity, gamma, and distance. Numerical integration is used to calculate the time in the vessel system. There are large swings in time aboard the vessel. In this case, the acceleration is intermittent and confirms the methods and results. Both methods show that when the system speeds are the same, time and the occupants' ages are the same. If we look at a car 100 light years away, but moving at the same velocity as us, and it accelerates to 10 meters per second, its clocks will advance by 105 seconds according to the Lorentz transforms. The reference clock stays synchronized with our own. Another observer only 10 light-years from the car only sees a change of 10.5 seconds, and an observer at the site sees no change. The only way to explain these effects is that they are distortions caused by the properties of light. Only the observers inside a system believe that the light travels the same distance both to and from a mirror. Observers in every other frame believe otherwise. The one-way speed of light and Doppler explain the observations without resorting to mystical forces.